If the series of absolute values of the terms in this series converges, then this series here converges absolutely. Otherwise, we say that this series converges conditionally. And the series can also diverge. So for example, if we consider this alternating series, then we designate this term as an, and this term here we designate as bn, which is the absolute value of an. And therefore, we can check if the series bn converges, and if it converges, then this series here converges absolutely. If a series A converges absolutely, and the sequence B is any arrangement of the sequence A, meaning that we can rearrange and group the terms in A in any order, then the series B will also converge absolutely, and the sum of series B will be equal to the sum of series A. And we'll show this in an example problem. Let's determine if this series converges conditionally, absolutely, or diverges. Well, we designate this term in the series as an, and this term in the series as bn, which is the absolute value of an. And now we check if the series an converges conditionally using the alternating series test. So in this test we just check if bn is greater than 0 for all n, which is true. And then we check if bn is greater than bn plus 1 for all n above some integer. Well, as we can see, 1 on n is greater than 1 on n plus 1 for all n. So this is satisfied. And then we check if the limit as n goes to infinity of bn is equal to 0, which is the case. So in other words, so far, the series an converges conditionally. Now to check for absolute convergence, we need to check if the series bn, which is the absolute value of an, converges. Well, we know that this is a harmonic series, and that it diverges. So therefore this series converges conditionally. Let's check if this alternating series converges conditionally, absolutely, or diverges. So again, we designate this series as an, and the series of these terms as bn, which is the absolute value of an. And now using the alternating series test, we can see that 1 on n squared is greater than 0 for all n, and the current terms in the series are always greater than the next terms in a series, for all n greater than some integer. And we also have the limit as n goes to infinity of 1 on n squared equal to 0. So the series satisfies the check for conditional convergence. And now to check if it converges absolutely, we take the series bn, and we recognize that this is a harmonic p series with the exponent greater than 1. So this series converges, and therefore this series converges absolutely. Let's determine if the following alternating series converges conditionally, absolutely, or diverges. So we designate these terms in the series as an, and these terms as bn, which is the absolute value of an. And using the alternating series test, we can see that bn is greater than 0 for all n, and we can also see that the current terms in the series are greater than the next terms in the series, for all n greater than some integer. And we can also see that the limit as n goes to infinity of Bn is also 0. So the series satisfy the checks for conditional convergence, and that the check if the series converges absolutely, we need to check if the series of Bn terms converges. And you can check that using the limit comparison test, and I'll leave that for you to check that if this series converges, then this series would converge absolutely. And post your answer in the comments. The following series converges absolutely, and we're asked to show that by rearranging the terms, the resulting series is the same sum. Well, this is an alternating geometric series that can be written as follows. And the most obvious way of rearranging this series is by grouping the positive and negative terms together. So this is one series, and this here is another geometric series where we factor out the negative sign. So this geometric series has a value a equals 1/2 and a ratio of -1/2. And this geometric series has a is equal to 1/2 and the ratio between the terms is 1/2 squared. And for this series over here, we can see that a is equal to 1/2 squared, and the ratio is also 1/2 squared. So really think about this. And given that absolute value of all the ratios is less than 1, then every one of those series has a sum that can be written as a on 1 minus the ratio. And now you can verify that this series and the difference of the sums between these two series has the same value. So post your answer in the comments.